Experience the sun like never before, unraveling the mysteries of solar storms in stunning detail. Imagine gazing at the sun where solar storms and dynamic eruptions come to life in breathtaking clarity. For the first time, thanks to a groundbreaking stability technique for telescopes, scientists can observe the sun's corona with incredible precision. The new method reveals intricate structures that span just a few dozen miles across. Providing nearly cinematic visuals of these celestial phenomena, the technological marvel known as adaptive optics for the corona achieves an astonishing resolution of approximately 39 miles at the sun's vast distance. This system is not just about pretty pictures. It plays a vital role in monitoring the rapid changes that directly influence space weather. The detailed images showcase delicate strands of cooling plasma, elegantly twisting formations known as prominent structures, and fleeting plasmoids that dissolve shortly after solar flares. Remarkably, these incredible visuals are not produced during unique eclipse events. They come from regular observations conducted by a ground-based telescope, utilizing real-time corrections for atmospheric disturbances. Why understanding the sun's corona is crucial. Lead researcher Dirk Schmidt from the U.S. National Science Foundation's National Solar Observatory spearheaded the development of this impressive technology at Big Bear Lake. Collaborating with experts from the New Jersey Institute of Technology's Center for Solar Terrestrial Research, Schmidt is at the forefront of solar observations. By achieving clearer views at smaller scales, this innovative imaging technique addresses a long-standing conundrum in solar physics. Why is the corona's temperature in the millions of degrees, while the layer beneath, known as the photosphere, is only about 10,000 degrees? This perplexity is affectionately termed the coronal heating problem. Existing spacecraft sensors, such as the Atmospheric Imaging Assembly on NASA's Solar Dynamics Observatory, capture the entire solar disk at a resolution of 1.5 arcseconds and a cadence of 12 seconds. However, they fall short of the fine angular fidelity provided by powerful ground telescopes, equipped with enhanced correction technologies. This new adaptive optics method significantly bridges that gap, unearthing the tiny strands and clusters that theoretical models of solar heating and cooling have long pointed to. A breakthrough in image clarity. The Earth's atmospheric turbulence severely blurs our telescopic images of celestial bodies like the sun. Luckily, we have developed methods to correct for this distortion, explained Schmidt. The Coronal Adaptive Optics System, CONA, constantly reshapes a specialized mirror at an impressive rate of about 2,200 times a second. It utilizes a tailored sensor attuned to pick up hydrogen alpha light, enabling it to focus on intricate features at the sun's limb, points where previous systems struggled to maintain stability. Previous solar adaptive optics technology excelled when observing the vibrant solar disk, but lost efficacy at the faint edges of the corona. CONA has been meticulously engineered to concentrate on less luminous coronal structures, ensuring that corrections are made on the specific areas of interest. This ensures stable imaging during quick bursts of observation. Operating at the telescope's diffraction limit of approximately 1/10 of an arcsecond, the team was able to capture features that are under 100 kilometers wide, including a tightly coiled plasmoid that appeared and disintegrated in the aftermath of a moderate solar flare. These observations hint at rapid magnetic topology changes, a phenomenon known as magnetic reconnection, which can produce small disturbances and energy releases in the sun's magnetic field. Discovering the significance of coronal rain. The telescopic precision allowed researchers to dissect coronal rain, transforming what was once a fuzzy image into a clearly defined structure. Many strands were detected near the telescope's resolution limit, with some appearing even narrower in the raw data. This detail is crucial because coronal rain serves as a direct indicator of how and where energy is transferred along coronal loops. with models predicting a vast array of sizes and cooling times correlated to specific heating mechanisms. Thomas Shad, an astronomer on the observing team, noted that raindrops within the sun's corona can be narrower than 20 kilometers. Based on the most detailed images of coronal rain captured to this point, coronal rain forms when the superheated plasma in loop structures becomes thermally unstable and condenses, representing a phase transition that has been linked to the delicate balance between heating and cooling processes in various active solar regions, an unexpected revelation following a solar flare. During one observation session, the team witnessed a rapid-moving, narrow plasmoid that formed near the top of post-flare loops and then dispersed into smaller fragments within minutes. This spectacular event would have appeared significantly less impressive had it been captured at a lower resolution. The intricate threads and sudden cessation of the plasmoid's motion indicate a complex interaction between magnetic forces and pressure, an embodiment of the classic principles of magnetohydrodynamics at play. Vasil Yurcheshin, a research professor at NJIT CSTR and co-author of the study, remarked, "These represent the most detailed observations we've ever obtained. We are still understanding what these features are. Such uncertainty can be beneficial as it highlights the scales where existing models need enhancement, guiding future spectroscopic studies that will enhance our comprehension of temperature distributions and flow dynamics in the corona." The future of solar observation and understanding. Currently, the CONA system operates at the Good Solar Telescope in California, and there are plans underway to apply this revolutionary technique at the 4-meter Daniel K. Inouye Solar Telescope, situated in Hawaii, which promises to further refine observable scales. Combining these high-resolution images with polarimetry at such a large aperture could enable routine assessments of coronal magnetic fields and their rapid fluctuations. However, transitioning to larger instruments also necessitates a focus on speed, as dynamic features can change drastically in just a fraction of a second. This is a challenge that the field of solar observation is eager to tackle now that coronal adaptive optics is transforming intricate structures from theoretical constructs into tangible data. This research has been published in the journal Nature Astronomy. Did this ignite your curiosity about the wonders of the sun and its corona? Join us in the conversation. What do you think about these new discoveries, and how do they challenge our understanding of solar dynamics? Feel free to share your thoughts in the comments below.